Hi, my name is Brian Caffo and welcome to the lecture on t-confidence intervals. This is part of the Coursera Statistical Inference class, which is part of our Coursera Data Science specialization. The class is co-taught with my co-instructors Jeff Leake and Roger Peng. We're all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. In the previous lecture, we discussed creating confidence intervals using the central limit theorem. All of the intervals we discussed took the form of estimate plus or minus a quantile from the standard normal distribution times the estimated standard error of the estimate. In this lecture, we're going to discuss some methods for small samples. Notably, we're going to talk about student or Gosset's t-distribution and t-confidence intervals. These intervals are going to be of the form estimate plus or minus a t-quantile times the standard error of the estimate. So the only change is we've changed this z-quantile to a t-quantile. The t-distribution has heavier tails than the normal distribution, so these intervals are going to be a little bit wider. These are some of the handiest intervals in all of statistics. And if you ever want to rule between when to use a t-interval or a z-interval for the cases where both are available, simply use the t-interval, because as you collect more data, the t-interval will just become more and more like the z-interval anyway. We're just going to cover the single and two-group version of the t-interval. In our regression class, we'll cover some other t-intervals that come in handy as well. The t-distribution was invented by William Gosset under the pseudonym Student in 1908. He worked for the Guinness Brewery, and in fact they didn't want him to publish under his real name, so he published under the pseudonym Student. So we're often talking about the student's t-distribution or the student's t-test. The t-distribution has thicker tails than the normal. Unlike the normal, which is indexed by two parameters, the mean and the variance, we really only talk about the t-distribution as it is centered around 0 with a standard formula for the scale. It's only indexed by one parameter, the so-called degrees of freedom. As these degrees of freedom increase, it gets more like a standard normal. The reason for the t-distribution is as follows. If we take x bar, subtract off the mean, and divide it by the estimated standard error for IID Gaussian data, it in fact is not Gaussian distributed. If we replaced s by sigma, it would be exactly standard normal. However, when we replace sigma by s, it no longer has a distribution as that of a standard normal. Instead, it has a t-distribution. As n increases, this distinction is irrelevant. However, for small sample sizes, the difference can be quite large. And so if you use a standard normal for small sample sizes, you can get, for example, confidence intervals that are too narrow. Our interval winds up to be x bar plus or minus the t-quantile with the degrees of freedom n minus 1 times the estimated standard error. We'll go through some examples, and I hope you'll get the hang of it. Here I use RStudio's manipulate function to show the t-distribution as it overlays over the normal distribution for varying degrees of freedom. Here I have it for 20 degrees of freedom, and you can see they're quite similar. As I draw the degrees of freedom down, you can see that the t-distribution gets to the point where it has heavier tails. Well, it always has heavier tails, and it looks like a normal distribution, whereas if you were to squash it down, sort of squash it down right there, and the extra mass had to head out in the tails. It's a little bit hard to see the impact because so much of this plot is devoted to the peaked part of the distributions where they're actually fairly similar. Let's plot the quantiles. So what I'm showing in this plot now are the quantiles of the t-distribution by the quantiles of the normal distribution starting at the 50th percentile. So for example, we start at 0, and since at the 50th percentile, since both distributions are symmetric about 0, you see that 0 is the 50th percentile, so this plot goes through the point 0, 0. I don't plot percentiles lower than the 50th percentile because the distributions are symmetric and that information is redundant. What I've drawn here are reference lines at the 97.5th quantile. This will always be around 1.96 for the standard normal distribution, but can be quite a bit larger for the t-distribution. For example, right now with 2 degrees of freedom, we get a t-quantile that is over 4. Now, let me emphasize though, with 2 degrees of freedom, that would mean in our t-interval that you only had 3 data points in order to estimate your variance, which is not too many. Let's bump it up to 20 degrees of freedom. And now what we see is that the t-quantiles are much closer to the normal quantiles. Right here in this light blue reference line is an identity line. If the t-quantiles were exactly identical to the normal quantiles, they would just fall on that line. I have again at 1.96 and the relevant t-quantile, I show the reference lines here. So this distance right here is exactly the distinction between the two intervals, where now with the t-interval we're going to have a quantile that's slightly larger than 2, whereas for the z-quantile we're going to have one that's slightly smaller than 2. This can make a fairly sizable difference in the intervals and often can make the difference between the interval containing 0 versus the interval not containing 0. And nonetheless, this is why we use the t-distribution. This plot, this quantile plot, is such that this t-interval, the t-quantile, is always going to be above this blue reference line, which is effectively saying that the t-constructed confidence interval will always be wider than the normal interval, which makes sense. We have an extra parameter that we're assuming we're estimating, the standard deviation, and so it would make sense that that uncertainty would cause us to have wider intervals. So here I give the code for overlaying the two densities, the t and the normal distribution, where you can use the slider to change the degrees of freedom. It requires the use of the package manipulate by RStudio. You have to be working in RStudio to use manipulate. Here I show you how to do it where you just focus in on the quantiles. So again, try out this code for yourself. Let's go through a couple notes about the t-interval. So the t-interval technically assumes that the data are IID normal, though it's very robust to this assumption. Basically, whenever the distribution is roughly symmetric and mound-shaped, the t-interval will work fairly well. If you have paired observations, for example, when you measure something once and then the same unit a few days later or for a second measurement, and we'll go through some examples, you can use the t-interval to analyze this kind of data by taking differences or differences on the log scale. For large degrees of freedom, the t-quantiles become exactly like that of the standard normal quantile, so the t-interval converges to that of the normal interval, the same one that you would obtain with the central limit theorem. Because of this, instead of picking between the t-interval and the normal interval, I always say just use the t-interval. For distributions that are skewed, in other words, distributions that look like, for example, that would be a skewed distribution where some of the mass is pulled toward the right. The spirit of the t-interval assumptions are violated. And so you could either work on this data on the log scale, where logging will often take care of the skewness of the data, or you can use other procedures, for example, creating bootstrapped confidence intervals. Nonetheless, it simply doesn't make sense to use the t-interval for skewed distributions because in a lot of ways it doesn't make sense to center intervals for skewed distributions at the mean. Also, I would add for highly discrete data like binary or Poisson data, other intervals are available and it's probably preferable to use them to the t-interval. In R, typing data sleep brings up the sleep data that was originally analyzed in Gosset's Biometrica paper. This shows the increase in hours slept for patients on 2 sleep medications. R treats the data as 2 groups rather than paired, but here we're going to treat the data as if they were paired. Here, data sleep will load the data. Head sleep will print the first few rows of the data frame. The variable extra is the extra hours slept. Group is a group ID, and ID is a subject ID. So 1 through 10 will give you subjects ID'd 1 through 10. Observation 11 is subject ID 1 again, and so on. Here I plot the data, and again the code for the plot can be found in the R Markdown file. I've connected each subject with a line. I think it's pretty clear here the benefit from acknowledging that these are repeat measurements on the same subjects. If you do not acknowledge that, then what you are comparing is this variation, group 1 variation, minus this variation, group 2 variation. If you do acknowledge that, then you are comparing these subject-specific differences when comparing across groups. The variation in these differences is much lower because observations within a subject are quite correlated. Here I grab the first 10 measurements, which are subjects 1 through 10, and here I grab the latter 10 measurements, which is subjects 1 through 10 on the second medication. The difference then is group 2 minus group 1. Here, the vector-wise subtraction making sense because I grabbed them in the specific order. The mean of the difference is just mean, and the standard deviation of the difference can be obtained with the function SD. Here, I define n to be 10. My t confidence interval can be given like this. It is the mean plus or minus the relevant t quantile evaluated at n-1 degrees of freedom times the standard error of the interval. Of course, we don't want to do this every time, so we can just do the function t-test of difference and t-test where we pass it the 2 vectors and give it the argument paired equals true. Or you can actually give it a form of model statement where you say outcome extra is a function of the group where paired equals true evaluated for the data frame sleep. I formatted these results a little bit because it gives you much more output than this, but I concatenated them into a matrix, and you can see that all of those commands give you about the same result. The difference in the groups being somewhere between 0.7 and 2.46. So because this is a confidence interval, the interpretation is that if we were to repeatedly perform this procedure on independent samples, about 95% of the intervals that we obtained would contain the true mean difference that we're estimating. This, of course, assumes that the subjects are a relevant sample from a population of subjects that we're interested in. Suppose that we want to compare the mean blood pressure between 2 groups in a randomized trial, those who received the treatment and those who received a placebo. Here, this is not unlike so-called A/B testing, which is probably the language is used most often in data science. Here, whether in A/B testing or in randomized trial, you are performing the randomization in order to balance unobserved covariates that may contaminate your results. Because you've performed this randomization, it's reasonable to just compare the 2 groups with a t-confidence interval or a t-test, which we'll cover later on. But we can't use a paired t-test because there is no matching of the subjects between the 2 groups. So we now present methods from comparing across independent groups. The standard confidence interval in this case is y bar minus x bar, the average in one group minus the average in another group, times the relevant t quantile, where here the degrees of freedom are a little bit hard. The degrees of freedom are nx plus ny minus 2, where nx is the number of observations going into the x group and y is the number of observations going into the y group. Here, this is the standard error of the difference. This S sub p right here I'll talk about in a minute, but it is multiplied times this factor here, 1 over nx plus 1 over ny raised to the 1/2 power. You'll notice that as we collect more data, 1 over nx gets very small and 1 over ny gets very small. The S sub p squared is the so-called pooled standard deviation. Or I'm sorry, S sub p squared is the so-called pooled variance. Its square root is the pooled standard deviation. If we're willing to assume that the variance is the same in the two groups, which would be reasonable if we had performed randomization, then our estimate of the variance should at some level be an average of the variance estimate from group 1 and the variance estimate from group 2. However, if we have different sample sizes, we'd like to weight the variance estimate from group 1 more than we weight the variance estimate from group 2, and that is exactly what the pooled variance estimate does. If in fact you have equal numbers of observations in both groups, nx is equal to ny, then the pooled variance is the simple average of the variance from the x group and the variance from the y group. But remember, this interval assumes a constant variance across the two groups. If that assumption is violated, then this interval won't give you the proper coverage. If there's some doubt, simply assume a different variance per group, which we'll cover later on in the lecture with a slightly different interval. Here I go through an example from Rosner's Fundamentals of Biostatistics book. This is a very good reference book. I quite like it. However, you don't want to put it in your backpack because it's pretty heavy. It's a very thorough book, about a couple hundred pages and weighing over 5 pounds, that is my guess. In one of the examples from this book, they're comparing 8 oral contraceptive users to 21 controls with respect to blood pressure. For the oral contraceptive users, they got an average systolic blood pressure of 133 milligrams of mercury with a standard deviation of 15, a control blood pressure of 127 with a standard deviation of 18. Let's go ahead and manually construct the independent group interval once just to churn through the calculation. When you tend to do this on your own, you tend to use t.test or something like that because you have the raw data. So the pooled standard deviation estimate is going to be the square root of the pooled variance estimate. There we need to take 15.34, the standard deviation from the oral contraceptive users, square it, 18.23, the standard deviation from the controls, and square it, and take their weighted average weighted by their sample sizes. So 7, which is 8 minus 1, and 20, which is 21 minus 1, from the two sample sizes minus 1, then divided by the sum of the sample sizes minus 2. That gives us a weighted average of the variances, where the group, the control group with 21, gets more impact than the oral contraceptive users with 8. Then I square root the whole thing because I want the standard deviation. Then my interval is the difference in the means, and then you always, whenever you're doing an independent group interval, you always want to kind of mentally think, which one is the first part of the subtraction? In this case, my oral contraceptive users are the first part. So I want to just remember that, because you don't want to look silly and suggest that controls have a higher blood pressure than oral contraceptive users when the empirical averages are exactly the reverse, just because you reverse the order in which you were subtracting things. Then I want to add and subtract the relevant t quantile, 27 degrees of freedom, which is 8 plus 21 minus 2, the pooled standard deviation estimate times 1 over n1 plus 1 over n2 raised to the 1/2 power. I get about -10 to 20. In this case, my interval contains 0, so I cannot rule out 0 as the possibility for the population difference between the two groups. Let's move on to another example. Let's revisit the example where we were looking at the sleep patients on the two drugs, but let's pretend that the subjects weren't matched. Okay, so I have N1 is from group 1, N2 is from group 2. Remember, in this case, both of those would be 10. I go through the construction of the pooled standard deviation estimate. I get the mean difference, and I get the standard error of the mean difference, which is the pooled standard deviation estimate times square root 1 over N1 plus 1 over N2. Then I collect together my manual construction of the confidence interval, which takes the mean difference and subtracts the t-quantile times the standard error of the mean. And then I do t.test, and I give it the first vector and the second vector. I tell it paired equals false, and then because I want the interval where I'm treating the variance in the two groups as equal, I do var equals true, and then I grab the confidence interval part. And then I want to compare it where the instance where paired equals true, just to remind us that ignoring pairing can really mess things up, and I want to grab the confidence interval. So here we get the interval, and my manual calculation, of course, exactly agrees with the standard t calculation, and you see that you get a very different interval than when you do the paired. If you take into account of the pairing, actually the interval is entirely above 0, where if you disregard the pairing, the interval actually contains 0. And I think when you actually look at the plot, it seems quite clear to me why that's the case. If you're comparing this variation to that variation, that's a lot of variability in the two groups. However, when you're matching up the subjects and looking at the variability in the difference, there's a lot of that variability is explained by inter-subject variability. Let's go through another example. The chick weight data in R contains weights of chicks from birth to a couple of weeks later. So to get it, you can do library data sets, data chick weight, and then I need to work with the data, and I highly recommend the package Reshape2. And I'll go through a little bit about some of the reshape commands and what they're doing. So the chick weight data comes in a format that is a long format. So it's the chicks lined up in a long vector. So if you want to take that long vector and make it a wide vector so that there's one column, say, for each time point that we measure the chick, then you want to do something like dcast, which is a function in the reshape package. So we want to dcast this chick weight data frame, and the variables diet and chick are the things that are staying the same, and the time variable is the one that's going to get sort of converted from a long format to a short format. So, and then I didn't like the names that it was giving it, so I renamed the latter couple of columns. Then I wanted to create a specific variable that is simply total weight gain from time 0. So I use the package dplyr, which then I take my data frame and I do the command mutate, and I want to give it my data frame again, and I want to create a new variable which is just the final time point minus the baseline time point, so the change in weight. And the change in weight is what I'm going to analyze from here on out. But let's actually look at the data first before we run our test. Here's the data for each of the 4 diets plotted as a so-called spaghetti plot. And again, the command for this plot, I use ggplot2. I've been trying throughout the lectures to convert all the graphics to ggplot2 since we teach ggplot earlier on in the specialization. Here we show each of the diets from baseline here to the final time point here for each case. So you'll notice there are some things that are potentially suspect, though they're a little bit hard to ascertain because of the varying sample sizes. For example, there appears to be a lot more end variation in the first diet than in the fourth diet, though again there's a greater number of chicks in the first diet than in the fourth diet, so it's maybe a little bit hard to actually compare the variability. I put a reference line here that is the mean for each of the groups. And I think, at least without any formal statistical test, it does appear that the average weight gain for the first diet does appear to be a little bit slower than the average weight gain for the fourth diet. Well, let's actually look at it using a formal confidence interval. Here I just show, rather than plotting the individual measurements, I show the end weight minus the baseline weight by each of the diets using a so-called violin plot. We're going to look at diets 1 and 4, and so we're going to be comparing this violin plot basically versus that violin plot. So our assumption of equal variances appears suspect here. In order to do the t-test notation, where you take an outcome variable like weight gain and use tilde times the explanatory variable of interest, for the t-test function for that to work, it needs to only have 2 levels for the explanatory variable. So that's what this subset command does, is that I merely take those records for which diet is in the variables 1 or 4, so omitting diets 2 and 3. And again, when you repeat this analysis on your own, you might want to compare 1 to 2, 1 to 3, 1 to 4, 2 to 3, 2 to 4, and 3 to 4, and do all possible comparisons. If you were to do that, I might add, you would also want to account for multiplicity, which later on in the inference class we're going to discuss how to do. Here I show the interval. Again, I'm collecting the results with an R-bind statement. Here I show the interval. I want paired equals false, which in this case paired equal true isn't even an option because the variables are of different, the vectors are of different length. But what I do compare here is assumption that the variances are equal versus the assumptions that the variances are unequal. And you do get different intervals. Both cases I'm grabbing the confidence interval. In the first one, I get negative 108 to negative 14. In the second, I get negative 104 to negative 18. Both cases, the intervals are entirely below 0, suggesting less weight gain on diet 1 than on diet 4. However, the specific interval does change depending on whether or not you have the variances are equal and the variances are false. Now, I don't know enough about the specific data set to ascertain whether that's a substantive change or not, but because it might be important, let's also cover the t-interval where you assume that the variances are unequal. So hopefully the formula for the unequal variance case looks pretty familiar to you. It's the difference in the means plus or minus a t-quantile times a standard error. The standard error is calculated assuming there's a different variance in each of the 2 groups. It turns out that if the x observations and the y observations are IID normal, potentially with different means and potentially with different variances, the relevant normalized statistic does not follow a t-distribution. Instead, it can be approximated by a t-distribution where we choose a rather elaborate formula for the degrees of freedom. Now, no one remembers this degrees of freedom calculation, and it's a very odd calculation because it doesn't just involve the sample sizes, but actually the estimated standard deviations and variances from the 2 groups. Nonetheless, if you plug in this potentially fractional degrees of freedom, you get a t calculation that very closely approximates the relevant distribution, which is not actually a t-distribution. And it turns out that it works well enough that I can give the statement that when you're in doubt, just use the unequal variance interval. On this page, I simply show churning through the calculations for the oral contraceptive example from earlier. You might want to go through this calculation just so you can at once convince yourself that you can plug into the standard deviation formula. Particularly, the degrees of freedom that you get in this case is 15.04. Nonetheless, typically when we want unequal variance t-test, we simply use the R command t.test with var.equal false, and that'll do the relevant t-test with unequal variances and produce the relevant t-quantile with unequal variances. So let's summarize what we talked about today. We talked about creating intervals using the t-distribution, some of the handiest intervals in all of statistics. When we have single observations or paired observations for which we've taken the difference, we use the t-interval to create intervals that are highly robust to the underlying assumptions regarding the distribution of the data. However, we have talked about a couple of cases where it's probably preferable to use something other than the t-distribution and t-intervals. For example, we talked about when the data are highly skewed, you may either want to take a log or look for different procedures. In addition, when your data is binary, you might consider something like looking at odds ratios, which we will cover in our generalized linear model component of the regression class. The same can be said for count data, where we'll talk about Poisson models and generalized linear models for rates, again in our regression class. For several of the other two-group special cases, the class Mathematical Biostatistics Bootcamp 2, also on Coursera, covers many of them.